And you guys have a handout because of the types of graphs we're going to need and stuff. I just figured that was easier. All right. So this section 5.4 is just sines and cosines. We'll get to the other 4 trig functions in section 5.5. So the next 2 days, just sines and cosines. Okay, so some definitions to start. When we graph sine and cosine, we're going to get these wave shapes, and we're going to see those in a few minutes. So there's a couple properties of the graphs that are a little bit different than what we saw with all of our other parent functions last semester. So the first is an amplitude. An amplitude is half of the height of the wave. Okay, so to calculate it by looking at a picture, you could figure out how tall the wave is and divide it by 2. We're going to see equations that are in the same form as that basic parent function we saw last semester. You guys recognize the A, B, C, D form here? For that big chart we did, the only difference now is instead of like an absolute value or a square root or something, it's going to be a sine or a cosine. It's going to be a trig function there. If you want to calculate amplitude, if you have the equation, it's just the absolute value of A. Okay, so it's either half the height of the wave or the absolute value of A, depending on which one you have. We call these functions periodic because they repeat their shape. After a certain period of time, they start and repeat that same shape over and over again. That's because we're graphing values that are on our unit circle. So we're going to see that every rotation, we know the values start over again. So that's going to help us find the period of a graph. The period is the smallest value of p when we're talking about the formula. We don't really use that though. It's more so how long it takes for the graph values to start to repeat. To calculate that, we're going to use 2 pi over b. And the b value, again, is coming from that basic equation we've seen before. Phase shift is a fancy way of saying our horizontal shift. So that's not new. It's just our left-right shift. And we know that that's the opposite value of c. So if it's a plus on the inside, it's moving to the left. We talked about that last semester. And if it's a minus, it's moving to the right. You also might see the word sinusoidal in like a word problem or something if you're doing your Math Excel. Sinusoidal just means wave shape. It's a graph that looks like a sine function. Okay. All right. So we're going to start by looking at our basic sine and cosine functions and just naming the properties before any transformations have occurred. Okay, so these are kind of like our parent functions, our basic functions for sine and cosine. All right, so at the top of your paper, this is the original graph of sine. The easiest way to tell the difference between sine and cosine, because you're going to see they're really similar, is where it crosses the y-axis. If it's the sine function, it's going to go through the origin. If it's the cosine function, it's actually going to have a y-intercept at 1. So we'll see that in a minute. Okay, so we're going to start by naming period, amplitude, domain, range, whether it's even or odd. All things from last semester. Well, domain, range, even, odd, last semester. All right, so starting with the period, we're talking about the period. We're talking about how long it takes as I go from left to right for the shape to start over again. So one full period of the sine function is a hill on the top and a hill on the bottom. And then the values start over again. So that takes me from pi to 2 pi. At 2 pi, then my values start over again. I see an upper hill and a lower hill. So we say the period is 2 pi. Now, why is the period 2 pi? What do we know about 2 pi on our unit circle? It's a full rotation, right? So wouldn't it make sense that after a full rotation, the values start over again? Right? Okay. Amplitude is half the height of the wave. How tall is this wave from bottom to top? It's 2. Half of that is 1. So we say the amplitude of this wave is 1. What's the domain, do you think? Yep, and we're going to practice using our interval notation with our parentheses. All real numbers, negative infinity, infinity. What's the range? Brackets or parentheses? Brackets. We do have points at -1 and +1. And even, odd, or neither. So even review was symmetric to the y-axis. Odd was symmetric to the origin, the ones you could flip upside down and it looks the same. Neither is neither. What do we think? This one is odd. It is an odd function. Okay, so what we're seeing when we see the sine function graphed is as we kind of rotate around our circle, what we're graphing is, think about our unit circle, sine is the y values. So if I start at 0 on my unit circle and I rotate around, think about what's happening with my y coordinate. Starts at 0, goes up to 1, goes back to 0, down to -1, back to 0. See why we're getting that wave shape? That's why this graph looks like it does. Okay. All right. Key points of the sine function are our special radian measures on our axes on our unit circle. This is not something that you should have to memorize if you know your unit circle. At 0, the sine is 0. At pi over 2, the sine is 1. At pi, the sine is 0. At 3 pi over 2, the sine is -1. And at 2 pi, it's 0. Okay, so we're not memorizing. It's coming from the circle. All right. I want you guys to do the same thing now real quick. You can find a partner if you want for the cosine function. Biggest difference here is it's starting on the y-axis at 1, like I mentioned. All right, so name the properties. I'll give you a minute. Shouldn't take super long on these ones. Let's see. All right, what'd you get for period? 2 pi again. Amplitude, domain, all reals, range, -1 to 1, even, odd, neither. This one is even, symmetric to the y-axis. The period here, I think it's easier for the cosine function to see a full shape. You just start at the peak, go all the way down and back to the top. Key points again, important. These are coming from our unit circle. These are all those radian measures. When we graph, you're going to see you're going to have radians on your x-axis at our quadrant angles, the ones that are on the axis. So when we graph the cosine function, we're thinking about the x-coordinate. That's what cosine is on our unit circle. So when I'm at 0, what's my x-coordinate? 1. That's why it starts at 1. Then as I rotate around my circle, my x-coordinate goes to 0, to -1, back to 0, and back up to 1. And then it starts over again because I've made my full rotation. Okay, and that's why, again, we're getting that wave shape. All right, so now the next slide that's on your paper, I put this in the notes. Do you guys recognize that from last semester? That has all the rules on it if you need to refer back to it. That's what we're going to be using to graph in a minute. Okay, so I think this one's on your paper. Yes? Okay. All right, we're going to just start with the function, the equation, and we're just going to name the properties right now, and then we'll do a graph in a few minutes. All right, so let's start with amplitude. To get the amplitude, we need to do the absolute value of A. What's the absolute value of A in this equation? What is A in this equation? -2. So the absolute value of -2 is 2. To get the period, we're going to do 2 pi over b. And we're using 2 pi because that's the original period of sine and cosine. That's why that's in the formula like it is. Now, b is the number that's in front of the x. What number is in front of the x? A 1. So 2 pi over 1. That b represents a horizontal stretch or shrink that's happened, which there isn't one, which means my period, my width of my wave has not changed. Next thing you need is your phase shift. Phase shift is the opposite of c. C is the number that's added or subtracted onto your x. So here it's positive pi over 4, which represents a shift to the right, pi over 4. So that's another way you could word that. The last one that we're going to find just from the equation itself is the range. Domain, we don't need a formula for. Domain is going to be always all real numbers for these functions. Range, though, is going to change from problem to problem. And there's two things that can affect the range, the height of a graph. First, a vertical stretch or shrink can do that. A reflection won't change the range. It'll just flip it upside down, but it'll still be the same values. And then a shift up or down could also affect the range. So those are the two things that we want to focus on. Your A value and your D value are the two things in an equation that will affect your range. Again, the A value, up or down, my stretch, and then my D value, up or down, my shift. We always start when we calculate the range with our basic range from our parent function, -1 to 1. Has there been a vertical stretch or shrink? Here, an A value. What's the A value? -2. And you don't need to worry about the negative. If you multiply by A, that's performing that vertical stretch. It's going to make it twice as high. Instead of from -1 to 1, it's going to go from -2 to 2. Okay? The other thing that can affect my range is a shift up or down. So to do my shift up or down, I just add on my D value, which in this case is what number? 1. So -2 moves to 1 and 2 moves to 3. So eventually, when we graph this equation, we should expect its domain to be all real numbers and its range to be from -1 to 3. And if you're doing Math Excel, you're going to see there's quite a few steps to getting the graph. If all you need is the range, it is much, much quicker to do this than to try to get the whole graph and name it from the picture. Okay. All right. I want you to try the next two with your partners. I'm going to remind you of something we talked about last semester, though. Are you allowed to have a number in front of the x? Like that 3. If there's something multiplied by your x, what should you do with it? Factor it out. Put it outside the parentheses. Okay, so I'll give you a minute. Try the next two named amplitude, period, phase shift, and range for each of these. Okay. All right, so double check how you factored it to start here. Dividing by 3 is the same as multiplying by a third. So imagine if I multiply 3x times a third, I get x. Pi over 6 times a third is why I'm getting pi over 18 there. You can kind of mentally distribute that back in to make sure you're back where you started if you're not sure if you did that part right, because that'll change your phase shift if you didn't do that correctly. So amplitude, absolute value of A is 5, period, 2 pi over B, so 2 pi over 3. Phase shift pi over 18, and then you can see, oops, it's kind of hidden there, the work I did for the range. I started with -1 to 1. I multiplied it by my A value, 5, and then I moved everything up a half because of my vertical shift there. And then down here, there is not a parentheses here, so that +1 is not inside the function, it is outside the function. I just emphasized it by putting the x in parentheses, but nothing really needs factored out on this one. They would put the parentheses there if they intended it to be inside the cosine function. So amplitude 2, period here, you can do 2 pi divided by 2 pi, so you get 1. Phase shift, there's no number added or subtracted with my x inside the function, so it's 0, hasn't moved left or right at all. And then the range actually ends up being the same as the top one. You multiply it by 2, and then you shift it up 1. Okay, any questions there? Just getting the properties from the equation. Okay, so what we're going to do now to get the full-on graph is we're going to do scale changes. Scale changes represent our stretches, our shrinks, and our reflections. And that's what the A and the B value in our equations do. And then we're going to do translations, which are our shifts, left, right, up, down. That's what our C and our D values do. Now, some of this should look familiar from last semester. The B value, the number that's inside the function, we use the reciprocal of it. Remember, because if it was a number like 3, it was a horizontal shrink. And if it was a number like 1/3, it was a horizontal stretch. So we do the reciprocal of B. It gets multiplied by my X because it's a horizontal stretch or shrink. My A value is a vertical stretch or shrink. So it gets multiplied by my Y. My C value, there's a negative there because it's the opposite. If it's a minus, we want it to move to the right. If it's a plus, we want it to move to the left. And it affects our x because it's a left-right shift. My D, we add on to my y because it's an up-down shift. So that should look familiar. Last semester we had put it together. We had said like 1 over b times x minus c was how you have changed the x coordinates for our parent function, and then we kind of threw them together for the y's as well. It's a little harder with the trig functions because we got all these radians we got to do calculations with, so we're going to split it into 2 pieces. So we're going to find our a, b, c, d values. We're going to do scale changes and then translations on those key points, the points that are kind of like the mins and the maxes on our wave shape. That's going to transform the function and allow us to make the graph. All right, so flip your paper over. We're just going to do 2 of these today. The first graph we're going to do only has scale changes. The second graph we're going to do only has translations, and then tomorrow we'll do a couple graphs that have everything all put together in it. Okay, so what we're graphing with is called the key point method. We are taking the key points of the original function and we are transforming them using the rules that we know about parent functions. When you get to a quiz or a test, it will be specific. It will say, use the key point method to graph these functions. You'll have to make sure you can fill all of this out. What you see on the top right there, that's called trigonometric graph paper. On the x-axis, you have your radians. On the y-axis, we have the values of our function that we're graphing. Okay, so let's label our values. -5 is what letter? A, B, C, or D? A. And 2 is B. You could always put it outside of the X if you want to, but there's no other number there, so we don't have to worry about factoring it out. Scale changes. The rule that we're going to use, it's reciprocal of B times X and A times Y. Okay, so the reciprocal of B will do my horizontal stretch or shrink. Reciprocal of B here is 1/2. Is going to get multiplied by my X's. So that's going to do a horizontal shrink. That's what we want it to do. A times Y. -5 times y. That's going to do a couple things. It's going to stretch it, make it 5 times as tall. The negative is also going to flip it over the x-axis for it. It's going to do it all at once. Key points. We are graphing a sine function. The x-coordinates don't change. The x-coordinates are your special radian measures around your unit circle. You don't have to memorize this if you know your unit circle. If you can just imagine I start at 0 and every 90 degrees around I name those radian measures. Then for the y's, this is the part that's going to change from one function to the next, you name the sine of that radian measure. Again, if you know your unit circle, you know these. The sine is the y coordinate on your unit circle, right? So what's the y coordinate at 0 on the unit circle? Sine of 0 is 0. What's the sine of pi over 2? 1. The sine of pi, 0. The sine of 3 pi over 2, and 2 pi, 0. Okay, so you know those. They're on your circle. All we need to do now is the math. All my x's, I'm going to multiply by 1/2. All my y's, I'm going to multiply by -5. If I multiply by my x's by 1/2, I get 0, pi over 4, pi over 2, 3 pi over 4, and pi. If I take my y's and multiply by -5, I get 0, -5, 0, 5, and 0. After you've completed whatever transformations are in the equation, here it was just the scale changes, we're going to plot those points. So 0, 0 is obviously the origin. Okay. When we graph pi over 4, -5, notice here's pi. So pi over 4, just think of it like a fraction. It's 1/4 of the way to pi. We're going to make a point at -5. Okay, so quarter of the way over, I'm going to go down to -5. Halfway to pi, I'm back at 0. 3/4 of the way to pi, I'm at 5. And then back at pi, I'm at 0. And you guys should be seeing a wave shape happen. It's always going to be that sinusoidal shape. And your points should be approximately equidistant from each other, okay? So you don't want like 2 points that are super close together and then 2 that are really, really far apart. That's bad. All right, so you want to connect it the best you can with a curve shape. Okay. And then what you have there is one period of this graph. So often when you graph these, they'll ask you to graph a period with points, which we have. You can then sketch another one. we just assume that that shape continues. So I could do the same thing, for example, to get to 2 pi. And this would really cover the entire graph. We're not going to worry about that. We're just going to put arrows on either side to show that it extends forever in either direction. Be careful with your arrows. Make sure your arrows don't go below the minimum point or above the maximum point. You might have to turn them around if you're at the top or the bottom, because we know that this graph is never going to get higher or lower than -5 and +5 respectively. It's just going to bounce between those two numbers forever. Okay, so naming the properties. You guys can use the picture to name the properties or the equation. Sometimes the equation's easier. For example, period, I would just do 2 pi over b. And what was my b value here? 2. So 2 pi over 2 is pi. Do you see that in the picture? That the length of one wave from start to finish is pi units wide, pi units long, okay? Amplitude, you can think of it as half the height of the wave or the absolute value of A. The height of this wave is 10, divided by 2 is 5. It's also absolute value of -5. What's the domain? Negative infinity to infinity. What's the range? Easier now because we have the picture, -5 to 5. The only thing I don't have on here is phase shift. What's the phase shift? 0. That's our C value, which we didn't have one. Okay, and I'll show you tomorrow too how you can check this with your graphing calculator. You can definitely check this with Desmos if you want to. You just have to change your axes to in terms of pi, which is a little harder. It's not too bad on your graphing calculator though. All right, let's do one more quick one that has shifts, left, right, up, down, same sort of idea. Okay, so here I don't have an A, I don't have a B, but I have a C, and I have a D. Okay, so those are my left-right shift and my up-down shift, respectively. T stands for translation. The rules for the translations are x minus c, y plus d. The x minus c will move it left-right in the approximate way it needs to go, and then y plus d will move it up-down. All right, so my translation for my x-coordinate is going to be minus pi over 3. That's going to move it left pi over 3 units. And then the plus d, it's going to be y plus 2 here, because it's going to move it up 2 units. Phase shift is listed here, so let's go ahead and name it. What's the phase shift? Opposite of C is what? Negative pi over 3. You're going to see it in the translation rule when you write it. Negative pi over 3 just means left pi over 3. Okay, key points are going to start the same, whether it's a sine or a cosine. 0, pi over 2, pi, 3 pi over 2, 2 pi. Just our special radians, every quarter rotation around our unit circle. Only difference now, the function we're graphing is a cosine function, okay? So we need to make sure that when we list the y-coordinates here, we're listing the cosines of those radian measures. So think about our unit circle. If I start at 0, what's my cosine? My cosine is 1. And then if I'm at pi over 2, my cosine is 0, okay? So you know this on your circle. And it goes 1, 0, -1, 0, 1. That is the only difference you're going to see between graphing a sine function and a cosine function, those values right there. All right, now we do the math. All of my x's, I have to take away pi over 3. All of my y's, I have to add 2. So 0 minus pi over 3, that one's not too bad. Negative pi over 3. Pi over 2 minus pi over 3, you guys might have to do a little, I don't know, sketch in the middle of your paper or in the margin or something. What do I need to be able to do that subtraction? What's common denominator? 3 or 6, right? I have a 2 and a 3, so I need a 6. So 3 pi over 6 minus 2 pi over 6 gives me what? Pi over 6. The next one might be able to do in your head, pi minus pi over 3. So think of it like 1 minus 1/3. What does that give me? Right? If I added it, it'd be 4 pi over 3. Oh, if it's 1 minus 1/3. I think you're thinking negative 1 minus 1/3. If you're doing it that way. There you go, 2/3. 2 pi over 3. Okay, 3 pi over 2. This one I can edit my little scratch work at the top there. If I had 3 pi over 2 minus pi over 3, I would have 9 pi over 6 minus 2 pi over 6 when I do it with common denominators, which would be 7 pi over 6. And then 2 minus 1/3. 2 pi minus pi over 3. What's 2 minus 1/3? You do that one in your head? You can write out with the common denominator if you need to. 2 minus 1/3. Well, 2 is how many thirds? 6/3. Minus 1/3 is 5/3. All right, 5 pi over 3. Y's are always easier. All we have to do is add 2. 3, 2, 1, 2, 3. There's your points. Plot them. Negative pi over 3. So about 1/3 of the way over. Oh, not there though. I'm up at 3. There we go. Okay. Pi over 6. So that's approximately 1/6 of the way to pi. I'm at 2. 2/3 of the way to pi. I'm at 1. 7/6. We know that's a little bit bigger than 1. So I'm past pi. And I go back up to 2. And then 5/3, we can think of that as 1 2/3. I'm back up to 3. Okay, and then that is one period of the graph. You can sketch a second one. Just do the best you can with it. Doesn't have to be perfect. And then like I mentioned before, just make sure those arrows don't go beyond the top point or below the bottom point. So we're going to kind of turn it around to show that it continues indefinitely in both directions. Period. 2 pi over b. There was no b here. There was no horizontal stretch or shrink. So my period is still 2 pi. From where it started to where it ended, it's 2 pi wide. Amplitude is half of the height of the wave. This wave is 2 units high. Half of it is 1. It's also a 1 for my a value. Domain is always all real numbers. Range 1 to 3 with brackets. Okay. Tomorrow we'll do maybe 1 or 2 more graphs, just putting it all together, and I'll show you how to check this stuff with your graphing calculator. If you guys want to start your Math Excel, you can tonight. Your 5-4 Math Excel is due on the 30th. So that'll be Sunday night is when your Math Excel is due.